Hello and welcome. Today, we're diving into one of the most fundamental concepts in any operating system, the process. We'll explore how a simple program on your disk becomes a live, running process in memory, how that memory is organized, and how processes communicate with the operating system itself. Let's get started. You've probably written a simple program before, like this "Hello World" example in C. When you write this code, it's just a text file. To run it, you first compile it. A compiler like GCC takes your code, Hello C, and turns it into an executable file, which is often called a .out by default. This executable file is a program, a static set of instructions stored on your disk, but it doesn't do anything yet. To bring it to life, you execute it. When you run the program, the operating system creates a process. A process is simply a program in execution. It's loaded from the disk into the computer's main memory, or RAM, where it can finally run. So what does this process look like in memory? It's not just a jumble of code. The operating system organizes it neatly into a memory map. The memory map has four main sections. Text. This is where the executable instructions, like your main function and any other functions, are stored. It's the code part of your program. Data. This section holds global and static variables. Think of it as the storage for data that exists for the entire life of the program. Heap. This is for dynamically allocated memory. When your program asks for memory while it's running, using a function like malloc in C, that memory is carved out from the heap. The heap typically grows upwards in memory. Stack. This is where local variables and function call information are stored. Every time a function is called, a new frame is pushed onto the stack. When the function finishes, its frame is popped off. The stack grows downwards. This entire memory space, from address 0 up to a certain limit, is called user space. This is the process's personal playground. But what lies beyond that limit? That's kernel space. This is where the operating system itself lives. The kernel is the core of the OS, managing everything from hardware to scheduling processes. Here's the crucial rule. A process running in user space cannot directly access kernel space. This is a fundamental security feature. It prevents a buggy or malicious program from crashing the entire operating system. However, the kernel can access everything, both its own space and the user space of every process. And what's really interesting is that every single process on your system sees this same structure. Each has its own private user space, but they all share the mapping to the same single kernel space. So, if a process can't touch the kernel's memory, how does it ask the operating system to do things, like printing to the screen or opening a file? It does this using system calls. A system call is a special protected function that allows a user process to request a service from the kernel. Let's look at printf, Hello World. When you call printf, it eventually boils down to a system call named write. To make this system call, the process executes a special hardware instruction called a trap. This trap instruction is like a doorbell for the kernel. It causes the CPU to switch from user mode to a privileged kernel mode. The CPU then stops executing the user program and jumps to a specific, predefined location in the kernel to handle the request. The kernel's write function then takes the Hello World string and sends it to the screen hardware. Once it's done, it switches the CPU back to user mode, and the process continues right where it left off. This is different from a regular function call, which stays entirely within user space and doesn't change the CPU's mode. Finally, let's zoom out and look at how the kernel itself is structured. There are two main designs. In a monolithic structure, all the operating system services, memory management, device drivers, networking, are bundled together into one large program. Pro, it's fast. Communication between modules is just a simple function call. Con, it's huge and complex. A bug in one small part, like a device driver, can crash the entire system. Examples: Linux and xv6. In a microkernel structure, only the most essential services run in the kernel. Other components, like the file system or networking stack, run as separate user space processes. Pro: it's more modular and secure. If the networking service crashes, the rest of the OS can keep running. Con: it can be slower. Communication between services has to go through the microkernel, which adds overhead compared to a direct function call. And that's a quick tour of processes. We've seen how a program on disk becomes a running process in memory, how that memory is structured into user space and kernel space, how system calls bridge the gap between them, and the different ways an OS kernel can be designed. Understanding these concepts is the first step to understanding how modern computers